Okay, welcome to the fourth video in the linear algebra and modeling sequence. This is called the dot product. We're going to get started here by redefining the vectors that we've been working with in the previous lessons, and this function vecplot that we previously defined. We're going to use it here in this lesson. So as a way to get to this idea of the dot product, we're going to start with two different properties of vectors: the length of a vector and the magnitude of a vector. So the length of a vector is just the number of elements in that vector. So the vector A has two elements in it. It has a length of 2. And even though H was a completely different vector from A and H have the same length, which we see here with this logical comparison. Now the magnitude is a different property. The magnitude is how far that vector goes in whichever direction it's going. And we can calculate it in R using this norm function with an argument of type equals 2. Now I should point out that this argument here is the string 2, not the integer 2. And it's very important. It won't work if you use just the number 2. You have to use the string 2. So let's go ahead and calculate the magnitude of A using this norm function, and this is the magnitude of A. This is how far A goes in the direction that it's going. And A and H do not have the same magnitude. They're different vectors. They travel a different distance. So we can think of magnitude as a Euclidean distance, and I'm putting the word Euclidean here because you will see it again. In the realm of data science. It's just a fancy word for the space that you're used to when you do regular algebra or geometry. You know, the regular Cartesian plane, the X and Y plane, it's a Euclidean plane, and it's just what you're used to, but it's a fancy name for it. So the magnitude of a 2D vector, this Euclidean distance, it's something that you've seen before, and I'm going to show that to you right now. So to do that, we're going to make component vectors for A along the X and Y axes. So I'm taking the values of A. So I'm taking A1, calling it AX, and A2, calling it AY, right here. And then I'm going to make an X vector that is AX and 0, and a Y vector that is 0 and AY. So I'm going to make those vectors. And then I'm going to plot those vectors, and I'm going to plot A. So here's A. We've seen that before. And then here's this X vector. It's the X component of the A vector. And here's this Y vector, the Y component of the A vector. And you should be thinking about, you should be remembering the Pythagorean theorem. That's what we're looking at here. So here's this Euclidean distance. The magnitude of A is equal to the square root of AX squared and AY squared, which is, you know, very similar to, maybe you remember this as A squared plus B squared equals C squared. So then C would be the square root of A squared plus B squared. So here we're doing the same thing. We're just using these components of the A vector. Now, one thing to point out real quick is when we're writing the magnitude, we will use these double absolute value symbols to denote the magnitude of a vector. And the other thing to take note of is that this formula actually works for p-dimensional vectors. It works for any number of dimensions. And you can probably figure this out for yourself by working on a 3-dimensional vector and see that it in fact works. Now, we have a fancy name for this. Remember, we used the norm function in R, and this is because this computation, this square root of the sum of the components squared, is called the L2 norm. And I'm using this fancy name because we will see the L2 norm again. We're going to see that as we continue our journey into data science. We'll see this name again. And, you know, as before, we're calculating it by using the norm function with an argument of type equals 2. And just to see that they're the same thing, we can take the square root here of the components squared, and we get the same value as if we did this norm function. So these are equivalent. This is how a norm of type 2 is calculated. So let's have a look at this first computation here. We've got the magnitude of a is equal to the square root of ax squared plus ay squared. And we can change that into the square root of ax times ax plus ay times ay. And what I want to think about is just the part that's underneath the radical. Remember, this is a radical. That's what this symbol is called. So we want the part that's just the part that's underneath the radical. Now this computation here is a special computation, and this is the dot product, where we take these components and multiply them together and then add them up. So the dot product is also known as the inner product. You might see this term inner product as you do your studies. And it's an operation that's defined over a vector space, but it doesn't give a vector back, it gives a scalar back. So you can think of it, and we've been talking about mappings, you can think of it as a mapping of two vectors to a scalar value. So here we've got a function, I'm taking in two vectors, and I'm getting a scalar back. So the f of u and v would be equal to alpha, where alpha is an element of just r, just the real numbers. So it's a function that takes in two vectors and gives a scalar back. And this might be a lot of math, but let's look at an example and you'll see that it's not that difficult. It's a pretty straightforward calculation. So if we've got these two vectors, u and v, then the dot product would be, and this is the symbol we use for the dot product. The dot product would be each element, so 1 gets multiplied times -3, 0 gets multiplied times 3, and -1 gets multiplied times -2. And then we add them all together and we get a single scalar value as the answer at the end. And so, yeah, this is how we write the dot product. We got, u times v, and it's equal to, this is a summation. This means add up all the ui components. And that's what we've got here. So here, this is how we do this calculation in R. We've got u is equal to this vector, 1, 0, -1, and v is this vector, -3, 3, and -2, and then we do this computation right here to get the dot product. And you see, in fact, we get -1 as the answer. So the symbol to do a dot product is, we've got this percent, and then an asterisk, and then a percent, and that's how we do the dot product in R. That's what's happening right there. So the dot product is a commutative operation. So the dot product of u times v is equal to the dot product of v times u. So just to come back to this magnitude, the magnitude of a vector is the square root of the dot product of a vector with itself. And that's a mouthful. That's a lot right there. But look at this. This is the dot product of a with itself. We have ax times ax plus ay times ay. That's the dot product. This would be equal to this dot product. So the magnitude is equal to the magnitude of a, and I'm just rewriting the same thing here, is equal to the square root of the dot product of a with itself. And we can see that right here. We've got, again, we're doing the norm of the type 2 norm of a, and I'm doing the square root of the dot product of a with a, and we get the same answer. This one's, it's rounded up. We only have it in 6 digits here, but it's the same answer internally. So just a quick note as we move on, a quick note on writing vectors. So these are the same thing. These are two different ways to write the same thing. And this is what's known as, we call this a column vector. So it's a column of values. And if we write it as this list here with commas in between it, we think of that as a column vector. And we'll write these often when we write it in math, we'll write it in boldface. Or when we write it in LaTeX, we'll write it in boldface. You know, like boldface U is thought of as being a column vector of U, this U column vector. So a vector that's written in this fashion, without the commas, we think of this as a row vector. You know, and to come back to data science, you know, we often think of column vectors as being a feature, you know, a single variable, and row vectors as being instances or values of all of the variables for a single measurement, a single instance in our whatever we're measuring. And we can change in between the two forms using this operation called the transpose. So if M is this column vector, 1, 2, 3, 4, then M transpose would be the row vector, 1 space 2 space 3 space 4. And R has this transpose operation that we can use to do this computation here. So I can do T of A is equal to A, and they're both true. Now this is sort of a wacky, I'm showing you this because this is sort of a wacky little thing. In R, sometimes it's going to just do this transpose operation for you, and sometimes you're going to need to like actually think about it. And I will show you when you don't need to think about it and when you do, but it is useful to think about row vectors and column vectors. So one reason why I'm showing you this right now in terms of the dot product is because I think that this is the easiest way to write a dot product. We often think of the dot product as the multiplication of a row vector. So this is a row vector, U transpose, times a column vector, U transpose V. So this is going to be equal to a row vector, 1, 0, negative 1, times a column vector. And I think that this is the easiest way to write a matrix, a dot product operation. Okay.